Okay, that's a circle. This one. All right, so let's start with something of a review. Okay, so we talked about exponential functions. We said exponential growth at the beginning. We said that the world uses that to say exponential growth is what kind of growth? Well, the world uses it just like in everyday language.
Increasing.
How increasing?
Rapid.
Rapid increase. That's kind of the way that the world uses the definition of exponential growth. But we said no. So first of all, it could be decrease, and it could be very, very slow increase. So what is the deal with exponential growth? What is the core mathematics that makes a function exponential? So I want everyone to write down a sentence that would describe what is true mathematical exponential growth. See if you can do it. I've done my best to try to hammer this idea over and over, so let's just take an informal quiz. If you were to write one sentence, exponential growth in mathematics is what? What is it, truly? If it's not rapid increase, then what is it? It's not going to be graded, so you don't have to cheat. This is just to see if you really get it. Okay, I want to hear some of what you wrote. So let's hear several of you. Who wants to volunteer? Thinks they got a good one. Or I'll just call on people. Marlene, please.
Okay, what I got out of it is that it's kind of like multiplying an output by an output.
Okay, multiplying an output by an output. Who else? So multiply. This is key. Multiplication is key. Yeah.
I just put down like a constant growth as the key factor that an output is multiplied by to get a new amount.
Okay, so there's this constant factor that the output is multiplied by to get the new amount. What else? Someone else? Yeah. Oh, that was awesome. Yeah, so that was the best one yet. Say it nice and loud. Yes, right? So it's some quantity that grows by repeated multiplication by a growth or decay factor. So if you said something about repeated multiplication by a growth or decay factor, you got it, okay? You got it. So the quantity grows by repeated multiplication by some growth or decay factor. Good, okay? All right, so let's just do a review problem, and that'll lead us into the new stuff, okay? So bacteria population started with 630 and grew by 45% every day. So here's some tasks for you. Determine the one-day growth factor, a function that outputs the population X days after there were 630, and the number of bacteria at 10 days. We all should be able to ace these questions. Everyone do it. Go. Okay, so here's a stack of homework. It's alphabetical. There's just one per person in this stack. Find yours, pass it on. Okay, last chance to turn in homework. It's okay. Well, it's folded. Last chance to turn in today's homework. Okay, Claudia, how about the one-day growth factor, Claudia? Did you get that? If there's 45% increase per day, what's the one-day growth factor? $1.45, she said. Right. Okay. How about the function? Scott. The function. Did you get the function?
Yeah, should be f of x equals 630 times 1.45 to the 10th, and then that's the x power.
To the 10th and to the x? If we just want the function?
Yeah, or just to the x.
Yeah, just to the x, right? So the 10th is now we're going to look at a particular output. Okay, so there's the function, f of x. Remember, the definition of a function is like an equation. You've got the notation on the left with the name and the input, and the whole thing means the output, and then on the right you have the rule. The definition is like it's in the form of an equation. Okay? At 10 days. Denise. And then how did you get that?
630 times 1.45 to the 10th.
And so I got, did you say, I got 25,883.
I think it's because I didn't put, I can, never mind, I typed it wrong.
Well, so, but you knew what to do, right? So,
Yeah.
okay, let's just review one more time how this works. How does this function work? This is what we talked about at the beginning of the unit. How this function works to calculate that number of bacteria according to just what we defined earlier as exponential growth. So, 630 is the number on day 0. What if we multiply that by 1.45? What do we get? That would give us the number on day 1, right? And if we wanted the number on day 2, what do we do? Multiply again. So if we want so every day that we multiply by 1.45, it gives us the new output. So if we want it on day 10, we will multiply 630 times the 1.45 10 times. But we just have, so exponent is just a shortened version of that. That's all the exponent is the shortened version of this most important thing right here. So we just have a way of condensing that with an exponent. 1.45 to the 10th. But we see this and we think, okay, there was 630, and then on day 1, times 1.45, and then on day 2, times 1.45 again. By the time we got to day 10, we multiplied 630 by 1.45 10 times. All review, right? Are we good? Should be good. Okay, so same setup. New question. How many days will it take the population to grow to 500,000 bacteria? Okay, so 500,000 bacteria. What is that related to our function? what is the 500,000 related to our function? Output, right? It's output, so it's like f of x, okay? It's like f of x. And then how many days is? Corresponding number of days is the input. So it's like we're turning the tables and we're saying, okay, if you had this output of 500,000, what input would generate that? Okay, so we could replace the f of x with 500,000, and we kind of work our way towards isolating x, right? Isolating x. First step, divide by 630, and so we end up with this. 793.65 equals 1.45 to the x. And so what happens here is there's really not like an algebraic step we can do to solve for the exponent x. It's like, do we divide by 1.45? No. Do we take the 1.45 root? No, that doesn't work. Do we take the 1 over x root? Well, we could, but that would just make it worse. Okay, so it's like, how do we solve for this x? If it's an exponent, if an unknown is an exponent, how do we solve for it? Okay, so here's the situation you run into. So in these exponential functions, if you know the output and you want the input, we kind of run into a roadblock. It's like an algebraic roadblock. Okay? All right, so we start like this. Would you agree that we could say, if we wanted to say x equals, we could do this? Do you agree? We could say x is the exponent of 1.45 that gives 793.65. Is that a fair statement? If we just wanted to start somehow, and we wanted to say x equals something, we could say this. We could say, well, x is the exponent of 1.45 that would result in or give 793.65. Okay, so in math, we have a shorthand version for that statement right there. We have a shorthand version for that statement, and that is the notation log. Okay, so by writing this thing right here, log, say this is log base 1.45 of 793.65. It's the exact same thing as this statement we wrote up here. The exponent of 1.45 that gives 793.65. Okay, so we might say this, that the purpose of a log is to solve for an exponent, but I actually want to emphasize a different way of looking at it than this. Not that it's solving for an exponent, but that a log is an exponent. Logs are exponents. That's what they do. They represent exponent. Any exponent that you would want to represent, you can represent as a log. So rather than thinking of it as some means of solving for an exponent, even better than that is a log is an exponent, or logs are exponents. Okay, so let's practice this. Any questions so far? Okay, and this particular log, this exponent, turns out to be 17.97 days, okay, to reach 500,000. And we'll get, so in terms of how to solve for that, we'll do that later. We want to first practice the idea of log, and then we'll come back later and I'll show you how you get this number is equal to that log, or that exponent. Okay, so here we go. So we had 1.45 to the x equals 793.65. And so that is absolutely equivalent to x equals the log base 1.45 of 793.65. These two mathematical statements are equivalent. They're the same, just different form. And they both say the exact same thing. They both say that x is the exponent of 1.45 that gives 793.65. This is the key right here. This is the whole ball of wax. That you see logs as this. So let's see how the one on the left does that. Well, x is the exponent. There it is. It's the exponent of 1.45. That gives or equals 793.65. Clearly, that statement is equivalent to the one on the left. And then also, we can look at the one on the right. X is, and then what are logs? Logs are exponents, and this particular log is the exponent of 1.45 that gives 793.65. So both those mathematical equations say the same thing. And that's the way we want to practice and see logs. Okay? So this is how we say it, and this is how we think it. Okay? So this is what we think, and this is what we say. The log base 1.45 of 793.65. Okay, so we're gonna practice this. So you got, for each of these, you got 2 tasks. The first thing is 1. I'm going to give you a log. The first thing you're going to do is describe in words exactly what exponent it is. And then 2, based on your description, write it as a mathematical statement. Okay, so the number 1 thing to do is describe in words. What exponent is that talking about? Okay, and here's the clue. It's like this. This is the model for it. Okay. And then once you think about that, oh, it's this exponent. Then you can write out a mathematical statement that reflects what you just did in number 1. Okay, so everybody try it. Where's the homework number stack? Still going around? Does it come over here yet? No. Okay. So everyone, get a partner and talk. So everyone practice speaking out. What exponent is this? And then, meaning here's your model. Okay, here's your model up here. And then you're going to write out a mathematical statement that reflects your response to number 1. Okay, don't worry about this for now. Okay, let's see how we did. Alex, what exponent is A? What exponent is A, Alex? Okay. So unless you're taking notes, you shouldn't be on your computer. Okay? So who else? Let's see. Laura, what exponent is A? Right. Okay. So just no. That I don't want you to. I want you to tell me what exponent it is. What exponent is A? Justin, did you get it? Okay. So A is the exponent of 5 that gives 25. This is saying A is the exponent of 5 that gives 25. And look, you can just read it left to right. You can just read it left to right. You see this? It's the exponent, logs are exponents, of 5 that gives 25. You see? You can read left to right. It's the exponent of 5 that gives 25. And so if A is the exponent of 5 that gives 25, what statement could we write? What could we say? So let's think about it. A is the exponent of 5 that would give you 25. So what would the statement be? James?
5 to the A equals 25.
5 to the A equals 25, right? It's the exponent of 5 that gives 25. And what is the exponent of 5 that gives 25? What do you do to 5 to get 25? Square. So A is 2. So that's what the log base 5 of 25 is. It's 2 because it's the exponent of 5 that gives 25. That's 2. Okay, does it make sense? More practice. Go. What exponent is z? And so what equation can you write? Flora, did you get it? Tell me.
Z is the exponent of 2 that gives you 16.
She wants the exponent of 2 that gives you 16. That's it. And so then if z is the exponent of 2 that gives 16, what's the equation?
2 raised to the z power equals 16.
She got it. 2 to the 6, z is 16. Okay, and what is the power of 2 that gives 16? 4. So that's the log base 2 of 16. It's 4. Because 4 is the exponent of 2 that would give you 16. One more. Go. Okay, homework stack number 2 has as many as 2 of your homeworks, and they're together. So it's alphabetical, and you should find your 2 together if you handed them both in. Christian, did you get this one? What is exponent is p?
P is the exponent of 4 that gives 1 over 64.
That's it. P is the exponent of 4 that gives 1 over 64. And what equation could you write?
4 to the power of P equals 1 over 64.
That's right. I gotta get this shift back. Almost there. So you said 4 to the p equals 1 over 64. Now to solve this one, it helps to change 1 over 64 to 1 over 4 cubed, so that the bases are the same. So we got 4 to the p and then 1 over 4 to the 3. So what exponent gives you 4 to the 3 in the denominator? Ever remember your rules of exponents? Wow, that has a sensitive touch today. So that's negative 3. So 4 to the negative 3 is the same as 1 over 4 cubed. So the log base 4 of 1 over 64 is negative 3. Because that's the exponent of 4 that would give you 1 over 64. Okay, anybody have a question? So let's look in your, if you look in your workbook. I'm looking for these. It looks like investigation 8. Can someone tell me what page these are on? You see this somewhere? Log base 2 of 4 equals y.
150.
Page 150? It says on page 150 at the top.
Yeah.
Top of page 150. So more practice. Practice saying, first of all, practice saying what each exponent is, okay? And then, based on what you say, rewrite it as an exponential equation, okay? So still want to keep practicing. What exponent is y? What exponent is t? What exponent is s, etc. Okay, so practice, so do the same thing we were doing before. Exact same thing, 2 steps. What exponent is it? And then write it in a different, write the mathematical result of that, and then determine what the exponent is. Did the first homework stack, oh, still moving? All done? Liv's not here, Mama's not here, Shannon's not here, all right. Is the rubber band? Oh, it broke, okay. And keep going on to, is there A through H there? You have A through H? Keep going on through H. Rapid fire, here we go. What exponent is y? Daniel.
2.
No. What exponent is y?
Exponent of 2. 4.
Okay, so you're tripped up because you know the answer. So if you're just looking at that log, what exponent is y? Just looking at that log right there and you didn't do any work. What exponent is y?
2.
Right. It's the answer. So you're just stuck on the answer, right?
Exponent of 2 is y.
That the exponent of 2, that would
4.
be 4. The exponent of 2, that would give you 4. Okay? What exponent is t? Melise, what exponent is t? According to this log right here, what exponent is t? Yeah? Right. It's the exponent of 9 that would give you 1 over 81. And is that negative 2? That's negative 2. All right. According to C, what's the exponent of K? Tiana? Yeah, that's, yeah. But just before you get to solving it. Right. And so what was the equation that you set up based on that? 3, the exponent of 3. Okay, so here's the deal with this. No matter what you raise, no matter what power you raise a number to, you always get a positive value. you always get a positive value. Because when we graph our exponential functions, like 3 to the k, well, if k increases, it starts at, our initial value is 1, right? This is like 1 times 3 to the k. So think of this function, ab to the x, okay? And we're going to graph it. So the initial value is 1, growth factor is 3, and then when you take negative values of k, you just get a number for closer and closer to 0, but never reaching 0. So no matter what value you put in for k, you always get a positive result. So no matter how you raise something to a power, you always get a positive result. Therefore, k. So what's our conclusion about k? What number k raised to as the power of 3 gives negative 2? Doesn't exist. So we can say D and E. There's no k. You raise a number to an exponent, you're always going to get a positive. You can raise 3 to a negative number. You can raise 3 to a fraction. You can raise 3 to a positive number. You can raise it to 0. You always get a positive result. So there's no way to raise 3 to the k and get negative 2. So there's no possible answer. Okay, what exponent is s? Taylor. What exponent is s?
S is the exponent of 5 that gives 10.
Right, so what equation could you write then?
5 raised to the s that gives 10.
That's it. It's the exponent of 5 that gives 10. Remember, you can read it left to right. That's the beauty of this. Logs are exponents. The exponent of 5 that gives 10. You can read it left to right. The exponent of 5 that gives 10. That's what that log is. Okay? So, what is the exponent of 5 that gives 10? All right, so what's 5 to the 1? All right, what's 5 squared? All right, so let's make a guess. So what exponent of 5 would give you 10? If 5 to the 1 gives 5 and 5 squared gives 25, then let's just make a guess at it. 1 point, closer to 1 or closer to 2? Closer to 1, so maybe 1.3, 1.4. So by the idea of what's going on, we can make a guess at it. Again, how do we get that number exactly? Oh, we'll get to that soon. Okay, so soon we'll figure out how to get exactly what, or a good approximation, a very good approximation for this particular exponent. The exponent of 5 that gives 10. Any questions on A through D? Yes, please.
We would be able to put s equals 5 to the square root of 10. And not to, just 5 square root of 10.
Okay, so you're thinking take the root of both sides, but really the root of what we need the s root of both sides to get rid of the s. It's not, this isn't the 10th root. So if you had x to the 10th equals 5, then we could take the 10th root of both sides to isolate the x. But when the exponent is the variable, you can't take a root of both sides. It doesn't work. You see that? And that's why we need logs. And if we could do something like that, then we wouldn't need logs. Okay? Questions on A through D? Okay. Still going. How about Mingfi? Can you tell me what exponent is P? What exponent is P? P is the exponent. Which exponent is it? Oh, Mingfi, your voice changed. Okay, Nancy, go ahead. Go for it. P is? Okay, and so what equation could you write? If P is the exponent of 7 that gives 18, then? Okay, and then we could, same thing. So P is going to be like, between what two numbers? 7 to the 1 is 7. 7 squared is 49. So it'd be between 1 and 2, right? Closer to 1 or closer to 2? Way closer to 1. So maybe 1.1 or 1.2. Something like that. Okay? Here's one we can do. What exponent is D? Colleen?
D is the exponent of 5 that gives 5.
So the equation is?
5 to the 5.
Again, nice easy one. And so what exponent is that?
1.
So the log base 5 of 5 is 1 because it's the exponent of 5 that will give you 5. Okay, let's look at this one up here. So this is a little different. This is saying what? 3 times an exponent. 3 times some exponent equals b. So what exponent are we talking about that we're taking 3 times? So what exponent is this right here? Javier, what exponent is this right here? Log base 4 of 22. No, I'm asking you what exponent is this? Log base 4 of 22. What exponent is it? Not b. This is we're practicing saying what these are, right? That's the exponent of what? Of 4 that gives 22. So there's some exponent of 4 that gives 22, and then 3 times that exponent is b. So what's another way to say then the exponent of 4 that gives 22 here? So that's really, we really need to isolate that. So what the exponent of 4 that gives 22 equals what? 3b? Not 3b. b over 3, right? So you could divide by 3, and now you've isolated that exponent. So now b over 3 is the exponent of 4 that gives 22. So now we can write an equation. So if the exponent of 4 that gives 22 is b over 3, how can we write it?
B over 3 is the exponent of 4 that gives 22.
And so what would the equation be? Yeah. You said, that's perfect. You said b over 3 is the exponent of 4 that gives 22. So b over 3 is the exponent of 4 that gives 22.
4 to the power of b over 3 equals 22.
That's it. That's the equivalent equation for f. Therefore, b over 3 would be between what? If we got 4 to something equals the 22, then b over 3 is going to be between what and what? So 4 to the 1 is 4. 4 squared is 16. 4 cubed is 64. So this exponent is going to be between 2 and 3. Closer to 2 or closer to 3? Closer to 2. Okay, so in terms of being fluent, going back and forth between the exponential version and the log version of these equations, there's nothing to memorize as long as you can interpret logs the way that we've been practicing. You can interpret logs like this. Oh, that's the exponent of 4 that gives 22, or this is the exponent of 7 that gives 18. Then you just think for a second or 2 seconds, and you write down this version. Like, oh, I need the exponent of 7 that gives 22. So there's nothing to memorize about. You can take this number and put it here, and you take this number and put it here, right? You don't have to do that if you really just understand what the log is. That's a better way to do it. Okay, so there are some special logs. Let's talk about those. Any questions on these examples? Goodness. Okay. So there's some special logs. Or log, so logs is short for logarithms. And every logarithm is what? An exponent. We can represent every exponent in the world as a logarithm, right? Because all we need is the base and then what it would give. Okay? So some special logarithms. So if you had log base 10 of 1,000. What exponent is that? What exponent is the log base 10 of 1,000? Jordan.
Are you asking like for the explanation?
Yes. I'm to ask you, explain to me what exponent that is right there.
It's on the 10.
That thing right there is the exponent of 10 that would give you 1,000. Okay? And so if we called it something, then we could set up an equation, right? And that equation would be, keep going. That's it. And what would x be? So what do you raise 10 to get 1,000? 3, right? 10 squared is 100. 10 cubed is 1,000. Okay, so since our numbers are structured on base 10, right? So when I write out a number here, right? So this is what? 6 tens. And this is 8 100s or 8 10 squareds. And this is 2 10 cubes or 2 thousands. Our number system, when we write out a number, it's based upon tens. So therefore, base 10 is a special kind of deal since we work in base 10. So this is equivalent to, if you don't see a base at all, it implies 10. So if you got your calculator, there's a button, and all it says on the button is log. That means base 10. So on your calculator, do log and do 1,000. So on your calculator, just type in log 1,000. And what do you get? It should come back with 3 because we're still talking about the exponent of 10. So just a log with no base showing is an exponent of 10. The base is implied to be 10. Okay? So this is called the common log. Base 10. And so because it's our system of numbers is in base 10, you don't, if there's no number there, you see it like there's a 10 there, okay? And what's a common log? Every common log is what? Every common log is what? It's not just base 10. Common log is an exponent of 10. An exponent of 10. Logs are exponents. Every common log is some exponent of 10. Some exponent of 10. Okay? Another one is log base E. Okay, so E is the natural base. E is a number like pi, right? So pi is what? 3.1415. Do you know that this year is the ultimate pi day? Have you heard about this? You know pi day is March 14th, right? So 3.14159, who knows more? What is it? 2653. I think that's enough. Does he have it right? So look, this year, March 14th, 2015, at 9:26 and 53 seconds. It's the ultimate pi moment. This will only happen once in your lifetime. It's on a Saturday. What kind of pie am I going to eat? Right. So is this A week from Saturday, so it's the second Saturday of your break. Okay, so you're all going to pay attention to this, right? In the middle of your spring break, you're going to plan, wait anxiously day by day for the ultimate pi moment, which will never happen again in your lifetime. Okay? What's that?
AM or PM?
I don't know. I suppose you could do both. You can celebrate this twice that day, right? At 9 a.m. and 9 p.m. Okay, but E is a number like that. It's an infinite, non-repeating decimal, okay? So it's a number like pi that is a fixed number. It never changes. E never changes. It's not a variable. It's a fixed number like pi is. And it has an infinite, non-repeating decimal. So it's 2.7, 1828, 18284, 5904. That's all I know. Just that many.
No more E than pi.
I know more of E than pi because there's a trick for remembering E. Okay, and so the point is it's a fixed number. E is a fixed number. It never changes, just like pi. Okay, and it's the natural base. Okay, it's the natural base, and so
It always says E10 on your calculator.
right. Okay, so should be another button that says like E, and if you hit it, you get E and it's ready for an exponent, right? Where's that on the calculator? Second what? Second ln has E built in, and as soon as you hit it, it's waiting for an exponent. Why? Because it's the natural base. It's ready for an exponent because it's used as a base. Okay? So if you do E and then hit 1, E to the 1, you should get this number. So E to the 1, that's just E. And that's this number down here. Okay, so because this is a special base called the natural base, there's a special log associated with it. Log base E is the same as natural log. So this is natural log. So when you see ln, that's the exact same thing as log base E. Those are equivalent. This is just a shortened version of this, just like log with no number is a shortened version of log base 10. So, what are natural logs? What are natural logs? Can anyone get it? In general, what's a natural log? What is it? What exponent is it? An exponent of E. Every natural log is an exponent of E. It's an exponent of E. That's what natural logs are. They're exponents of E. In this case, the exponent of E that would give 7. So we could say E to the A, or any variable you want, equals 7. So that A right there is the natural log, the exponent of E that gives 7, so it's natural log of 7. So your calculator has log built as a built-in button for log and a built-in button for natural log. Exponents of 10, exponents of E. But it doesn't have a built-in, just a single built-in button for any other base. Okay? So these are the two that you can just do quickly. A common log, an exponent of 10, or a natural log, an exponent of E. So this then is how we can we can use these two to solve for any log. Okay, so we're going to use common or natural logs to find a good approximation for any log. So the first one we had was in that initial example, So the way that we can do that is what's called the change of base formula. And this is what the change of base formula is. The log base, say, P of Q, or the exponent of P that gives Q, right? The exponent of P that gives Q is the same as the log base B of Q over the log base B of P. And we can choose B to be any base we want. That's the beauty of this. B is any base we want. Those are all B's. What? I'll make all my B's better. See if I can do this better. How about that? Those are the best B's I can make. They're all B's. So we can choose any base and create this ratio, and that will solve for any log. Okay, so what did we have to solve for the number of years to reach, what was it, 500,000 bacteria? We ended up with the number of years was the log base of 500,000. And what was the base? Nice and loud. 0.45? 1.45. It wasn't, okay, so it was something different here. Right, it was the 1.45, and then when we divided, we got 793. Thank you. So we needed this one. Why? Because we needed the exponent of 1.45 that gives 793.65. That was what we had right before that, right? Right before in that problem, we ended up with this. And we said, how can we solve for x? Okay, how can we solve? We can represent x as a log. That's how we can do it. If x is an exponent, we can represent it as a log. It's the exponent of 1.45 that gives 793.65, sorry. So, the exponent of 1.45 that gives 793.65. So we can use the change of base formula. And since your calculator has common log and natural log built in, we're going to choose one of those bases for B. What are the two bases we could choose in this formula? We're going to choose what? So we can use one of the built-in buttons on our calculator. 10 or E. So let's do 10 first. Okay? So it's going to be the log base 10 means you don't write anything. And so in the numerator, you're going to put the 793.65. And the denominator, you have to have the same base in the denominator, so 10. And then in the denominator, it's going to be your original base, right, is what you take the log of. So this is equal to, that's the exponent of 1.45 that gives 793.65. And is it 17, you get 17.97? So that's our exponent x, which is the number of years to reach 500,000 bacteria. Okay, so let's just see if it works by doing natural log now. So you should also be able to choose base E. So natural log of 793.65 over natural log of 1.45 equals you should get the exact same thing. Because you can choose any base that you want in this change of base formula. Any base that you want, as long as it's the same, will give you this original log that you wanted. Okay? So, pick your favorite and use it always. or alternate, whatever you want. It does, because they always give you the same thing. You can choose any base that you want when you rewrite with a change of base formula. Okay, so we have a way now for solving for exponents. Represent your exponent as a log, use the change of base formula, and it can give you a good approximation. What was one other that we had done earlier in class that we estimated? Anybody remember? Like, did we have the log base 5 of 10? I think we had that one. Log base 5 of 10. So how can you set it up with the change of base formula? That's equal to? You could do ln of what over ln of what? Ln of 10 over ln of 5. And we estimated this was like 1.1, 1.2. What is it, actually? 1.43. But that's just an approximation, right? It goes on. Okay, questions about the change of base formula. So this is how we can actually get a number out of these expressions of exponents, right? So we can express the exponent as a log, then we can use the change of base to get a number. So let's do an example. Okay, so here's some practice. So the amount of investment is determined by this function. Determine when the investment will reach $1 million. Okay? When will this investment reach $1 million? So what's our initial value of the investment? So the initial value is $41.86. And what's our interest we're getting per compounding period? So this T is number of compounding periods. So what's our percent per compounding period? 2.5% increase per compounding period. So in that scheme, how long will it take to reach $1 million? See if you can get an actual number of compound. So let's call it years. All right. So no, let's call it months. So T is the same months. So T is a number of months. Great. This is a really good return on your investment. 2.5% per month would be an amazing return on your investment. So how many months would it take for 400? This amount, 4,000, to reach $1 million. See if you can do it. How's the second step coming? Did it make it all the way? Is it?
Yeah.
Oh, maybe you missed one. Okay, Kyler, did you get started?
Not touched.
Can you get started? So this, how does this $1 million relate to this function?
You're multiplying by 2.5%, so per factor. So wouldn't the exponent be set up as log 1.05.
Are you doing too? You're going trying to do too much too fast. So let's just first decide: is this $1 million an input or output of this function? Output. So how can you set this up?
Oh, 1 million equals that function.
Equals. All right. Now what would you do? We're trying to figure out what t is. So what would you do? Divide. Okay, so we're gonna the first 1 million is the output, and we're trying to determine the input of this function that would give us an output of 1 million, right? So we're gonna start by dividing by 4186. And what do we get? So let's get a good approximation, good decimal for that. Nice and loud. One person. 2. Is there one more decimal place, just in case? How about that? Is that right? Cool. All right. Equals. And so here's our roadblock. How can we write what t equals? Well, you just say that t is the exponent of this that gives this. And then we write it down. It's the exponent of 1.025 that gives. Yep. So some of you have learned a technique of taking a log of both sides. That takes a lot longer. It's more steps. If you just say to yourself, oh, I got the exponent of 1.025 that gives me this, well, I know what log that is. The exponent of that gives that. And you just solved yourself like 20 or 30 seconds of all these steps taking the log of both sides. This is better. This is better. So if you've done that before, start doing it this way. Start thinking about the meaning of logs as an exponent. Okay? How do we solve that? Because we don't have a 1.025 base button on your calculator. So instead we do, I'll do common log. Log of 238.8584 divided by, so this is our change of base formula. It allows us to get a number for this exponent, right? It allows us to get a number for that exponent. And what do we get? 2. So, after 221 months, do you have $1 million? Not quite. So how many whole months would it take to reach 1 million? 222. 222. Divide that by 12. Quick. Divide by 12 is? 18.5 years. For a cool million from 4,000. It's a really good investment. Okay, web work and quiz on Thursday. Yeah.
Yeah.